A very good day to you and welcome back to my channel. So today we will be looking at visible spectrum, but before we go into that, I do have these two diagrams. Many of you are probably very familiar with what I'm presenting on this particular slide. So on my left, I have this scene from Tenki no Ko, and on my right, this is from Kimi no Nawa. What I want you to emphasize on this, I want you to look at the background of it. So the question that I need you to be able to think and answer is that why does the sky appears blue during the day, as you can see in that particular scene in Tenki no Ko? And if you look at that particular scene in Kimi no Nawa, you can see that when the sun is set or during sunset, you can see the sky actually becomes red. So my question to you is, why is the sky red? Why does the color of the sky change? So something for you to think about, and I will answer the question when we go through today's topic, and you will be able to find out the answer to that question. Let's move on to the next slide. Alright, so we are looking at visible spectrum for today. So it says the visible spectrum is the rainbow of colors that combine to form white color. So all of the colors combined will be of white color. It says that this visible spectrum is a component of electromagnetic radiation. If you still recall, we look at a range of what we call the electromagnetic radiation. They have different wavelength. So we have combination of different wavelength within the electromagnetic radiation. And electromagnetic, what it means is that you have a combination of electricity and magnets. And since here the color that make up the visible spectrums are red, orange, yellow, green, blue, indigo, and violet. So these are what we call the rainbow color. So I will highlight this. I'll highlight this for you. So we have red, orange, yellow, green, blue, indigo, and violet. It says when all the colors shine at once, they produce white color or white light. Moving on to the next slide. Alright, so looking at this particular slide here, we are looking at visible spectrum. So visible spectrum means that the spectrum that you can actually see. So if you can look at a particular object, you know the color of the object, you know that it is of the visible spectrum. So it says here at the top, each color of light is a wave with a different wavelength and frequency. The wavelengths of visible light are extremely small, ranging from violet light with wavelength around 400 nanometer through to red light with wavelength around 700 nanometer. And nanometer itself is very small. 1 nanometer is 1 times 10 power of minus 9 meter, which means that the wavelength is extremely small in that sense. It says that the wavelength of visible light are less than 1,000 of a millimeter long and about 100 width of a human hair. So the diagram that you can see at the bottom there, now use this to in a way to explain the question that I asked you before. And I was asking you the question of why does the sky become red during sunset? And that applies to when the sun is rising as well. Why? It has a lot to do with the change in that particular wavelength of the light. As you can see that at 700 nanometer, the color that you observe is red. And then at 500 nanometer, you will see it as blue. So to partially answer the question that I've asked, it has a lot to do with a process known as scattering, that there is an interaction between sunlight and air particles. So think about it. Do you think that there's more interaction between sunlight and air particles when the sun is rising or when the sun is setting? So in a way that can enable you to actually answer the question. Once again, I'll fully answer the question towards the end of the lesson. So think about the wavelength and how it can change depending on the day or depending on the position of the sun. So if the distance between the sun as the person looking or facing the sun increases, do you think that there will be change in the wavelength? If there is, do you think the color of the sky will change as a result? Alright, moving on to the next slide. So seeing in color, it says that some apples are red while others are green. This is because pigments on the surface of the apples determine their color. It says under white light, the apple looks red because it reflects red light towards your eyes and absorbs orange, yellow, green, blue, indigo, violet light. It says in reality, the red apple may reflect a little orange light as well, but this just affects the shade of red that you see. White objects reflect all visible wavelength of light, while black objects absorb all visible wavelength, which is true. And there is a saying that if you wear black clothes, for example, in a very hot day, you will feel very warm. And the reason for that is because the black shirt is absorbing all visible wavelength. As compared to you wearing a white shirt, the heat will not be stored as much as a black object because you are reflecting the visible wavelength of light. So in general, what this is telling us is that when that particular object is reflecting that light, you will be able to see it as that color. And that's the reason why leaves are green in color, because green light is being reflected. If you go out, for example, if you have a car that is gray, it is gray is because gray light is being reflected. If you walk out your house and you go to school, you come across a building that is blue in color, what does it mean? It means blue light is being reflected. So this is an experiment that scientists have actually done. If you look at this diagram on the right, and it says here that in white light, you will be able to see the object as what it is. So a white candle will appear as white, blue candle will appear as blue, green candle will appear as green, and so on. It says that the white candle reflects all colors. The blue, green, and red candles absorb all colors except the color they are. So a blue candle will absorb all light except for blue color, it will reflect blue colors. But if you are in an environment that is of red light, you can see the color that you observe will change. If you look at the white candle, you see the white candle and the red candle reflect red light and low red. And then it says that the blue and green candles absorb most of the red light and appear almost black, which is true. If that particular object in this case is red in color, it will reflect red light. If it's white in color, and we say that white light reflects all wavelength or all visible wavelength of light, so it means that it will also be reflecting the red light. And then in this case, the blue and the green will actually absorb the red light, and they will appear black. Okay, something for you to think about. Moving on to the next slide. Alright, so this slide is looking at primary colors. We know the three primary colors of light are red, green, and blue. And it says here, when you combine light of the primary colors in pairs, the three secondary colors are magenta, cyan, and yellow are produced. So looking at the diagram on the right, you can see you have blue, red, and green color. If you have a combination of red and blue, you get magenta. If you have a combination of blue and green, you get cyan. If you have a combination of red and green, you will get yellow. And if it's a combination of all colors, you will get white color. Alright, what this is trying to tell us is that let's say you have a blue object. If you are shining blue light at the object, it will reflect all the blue light because it's reflecting blue light for it to appear as blue. But at the same time, it will actually absorb red light. So if you're shining red light to blue, it will actually absorb the red light into it. And the same goes for those secondary colors as well. So if you have yellow color, for example, if you're shining red light, the red light will be reflected. If you're shining green light, the green light will be reflected because yellow consists of red and green. But if you're shining blue light, for example, the blue light will be absorbed. So anything that is not of that color will be reflected. Anything else or any other wavelength will be absorbed. So something for you to think about. So once again, as mentioned before, we have the three primary colors, and that's very important when we are talking about objects, for example. Which means that, and when we are talking about the sky, for example, if the sky is blue in color, it is reflecting blue light. If the sky is red in color, it's reflecting red light. And that's a lot to do with the difference in the wavelength. Moving on to the next slide. So it says here, color filters. A red apple absorbs all colors of the visible spectrum except red light. Similarly, a red piece of cellophane absorbs all colors except red light, which passes straight through. The cellophane acts as a color filter. So something that we have discussed. And it says here at the bottom, a color filter only allows light of its particular color to pass through to be transmitted. Color filters are used widely in photography and the theater to provide a range of lighting effect. So if you look at this diagram on the right, if you have this particular object, it says that if you have red filter, it will absorb everything but red. So red will be reflected, or it will not be absorbed by that particular object. And if you have a green filter, it will absorb the red light, so no light will go through. So that is the diagram at the top. If you look at the diagram at the bottom, if you have a yellow filter, it says yellow filter will let red and green pass through because yellow light is made up of red and green. So red and green light will be reflected. It will not be absorbed. But it says that if you have a red filter, the red filter now will absorb green light, but it will allow red light to pass through because red light will be reflected. So that is generally speaking on how absorption of and reflection of light works. Moving on to the next slide. Alright, so looking at this slide here, we are talking about color printing. It says that when all of the colors of light are added together, white light is produced. However, if you mix every color of pink pigment, then the final mixture will look dark and murky. As more pink pigments are added, more colors are absorbed rather than reflected. This type of color combination is known as subtractive color mixing. So, in general, what we know is that white light consists of a combination of all colors. But if you're actually mixing colors together, you see that the color becomes darker and murky because it has a lot to do with how the colors are now being absorbed rather than reflected because you have a lot of pink pigments that come together. Alright, and this is on color printing. To finalize today's topic on color, and to answer the question that I've asked you at the start of the topic of why sky is red during sunset, it has a lot to do with the scattering of sunlight, and in this case sunlight will interact with the air particles, and we know that red generally have a larger wavelength based on what we have discussed, and blue has a shorter wavelength, which means that red color, it will have a shorter or smaller frequency. And during the day, light will travels at a higher frequency because the distance is a lot shorter. But as the sun sets and the distance increases, the color that you observe in the sky will start to become red because of the increasing wavelength and the reduction in frequency. And because of the increase in scattering of light as well in the air, you will see that the sky will appear as red. So something for you to think about the next time if you have gone through, let's just say a film, and then you see that the sky becomes red, you will know what is the answer to the question. Thank you very much for watching, and I will see you soon.